Hello, everybody. Good morning, good evening, good afternoon, and thank you for joining this Neo4j Live, and particularly, obviously, a very warm welcome to Suleiman Sharif. Thank you very much for joining us today at the Neo4j live stream on talking about porting Global-Chem graph infrastructure into Neo4j. So I'm very excited about this. Hi, Suleiman. How's it going?
Hey, it's going all right. How about you?
Good, very good. Doing very well today. I'm very excited. So I'm looking forward to this session. I think it's going to be fun and interesting
Yeah.
and great for everybody. So a
So I
pretty
figured I get right into it, and then Alex, like, ask questions along the way. Feel free to interrupt me as we can just talk about it, like why I chose some of the things I did, and then because it might be a little kind of complicated, you know. So anything that you want to clarify, and I'll try to do my
Yeah,
best here.
yeah. Okay.
Yeah.
No, that sounds good. That sounds good. I can ask questions definitely. Before we dive into that, I wanted to make sure that everybody knows how this works generally. If you're watching this for the first time, then this is supposed to be interactive. So I'm not the only one that can ask questions, or everybody else can ask questions as well in chat. So if you watch this live, please don't hesitate. I try to make sense of a time where it fits and intercept with questions. So if you see something you want to know more about, then please type it in chat, and I can read those questions aloud. So Suleiman can answer them if possible. Maybe we have some time and space for this at the end, or in between. Whatever works. But yeah, this is supposed to be interactive, so please don't hesitate with questions, comments, whatever else you see
Cool.
and hear.
Yeah.
Yeah,
Alex,
I guess with that,
You can call me Saul, by the way. It's a
yeah,
quick and easy name.
that's easy. Yeah, okay. Saves 5 letters, so I guess it's fine.
It's important, you know.
4 even, only 4. Yeah.
Important in the days of online world, you know.
Yeah. Yeah.
Okay, so I I'll get right into what I was doing. So I created this thing called Global-Chem, and it was originally this relational database model that I built for chemistry molecules, and then I wanted to switch that into a graph database model, and then there was reasons for it. And then the second part was kind of creating this network of people behind this model, and then ultimately is then moving it into the cloud and having it interoperable with a lot of these machine learning platforms based in like either Azure or AWS or something like that. Is that and so I'll as we kind of go through this discussion, I'll talk about these each 3 aims, but then we'll demo it in the code, and so you can see how I progress through the code to get there.
Okay, sounds good. Do you mind clicking on the hide button at the bottom of your screen where it says, yeah, exactly this one there.
Okay.
Yeah.
So, okay, Alex, are you familiar with a relational data model and a graph and how it's used in industry?
Well, relatively familiar with the graph model, not as much maybe with the relational, only basics. But in the industry, probably I'm not very familiar, because I mean every industry does it a little bit different. So I guess your industry differs from my experience. So yeah, maybe explain a little bit.
Yeah.
Yeah.
So for me, relational database models are so like, okay. So I have this idea of like a vending machine, and let's say we want to store this in a record. We would say that this machine is some sort of entity, and then inside this machine we probably have some sort of items, and so we have this relationship here where we say like things can be inside this machine. Um, and so we have like items that we have, which are these like the Dasani water, the Gatorade, the Monster, and these all kind of like they're all like an item group. And so we also have another relationship which groups them as like, okay, these items belong in a group, and then they're inside the machine. And then each item has their own individuality. So this Dasani is just water. This Gatorade is some sort of um, sports drink or something. And then, so they have their own little metadata. Now, relational database models work because you have millions of vending machines and they all follow the same pretty much suit. And so it's very efficient just to have these relationships where they're predefined, where you know that these items are always going to be inside a machine.
Yep.
And so these models work very effectively when you start building workflows and building pipelines amongst the workflows where relationships are very predefined. Now, a graph model, however, is a little bit different, where the relationships are not as predefined. Let's take this instance of this vending machine in a very simplistic way, where each item, if let's say each item was unique, and each item would be stored its own metadata, or it could be
Mhm.
categorized as a drink, and then it had its own um, item data, and then it has each of those items then have a relationship to the machine itself. And so whatever that relationship could be, so this item could be inside the machine, or like let's say it leaves the machine, then it's outside. But you define each relationship individually, if that makes sense.
Yeah. Yeah, that makes sense. Yeah.
So that's the switch, is like how you define your relationships between relational and graph. Now, like it's not always going to be efficient to do that, um, because already, like if you have predefined relationships, it's very effective. Why would you need to switch to a graph model, right? Um, but there are going to be instances where the data is loose and the relationships don't exactly make sense. And so, like as you're building the database, something that's very malleable, this is where I think a graph database would really come in. Does that make sense?
Hmm.
Okay.
Yeah, I
So
mean that's what we see, right? I mean here at Neo4j, the more flexible, the more agile your system is supposed to be, the less likely a relation database is fitting the purpose.
right, yeah, and so this is kind of where it comes in as I started looking at chemical data. And so in chemistry, you'll always see these new trends. And so I'll take a little break to look at the graph here. So I wrote that package Global-Chem, and Global-Chem has
Do-
it's
yeah,
going with sorry.
yeah. Are you going to say what Global-Chem is so people know what it is? I when I talk to people about this, I said it's a little bit like PubMed for chemistry. Is that something you would say is true, or how would you describe Global-Chem as a concept?
So Global-Chem is an open source type of government
Hmm.
where basically we elect compounds based on how useful they are to a certain community. And
Okay.
it's based on what's common or what's valuable. So there's an old saying where, like, we don't need all the software in the world, we just need the best. And that's just, and
Yeah.
and that saying kind of follows through with chemicals as well. We don't need all the chemicals in the world. We just need the best for what we need it to do. Does that make
Hmm.
sense?
Yeah, yeah, yeah.
Now, that expertise can't come from me. So I studied organic chemistry when I was in college 10 years ago. And, I know my field and I've studied a lot of medicinal chemistry. So I spend a lot of time trying to design fragments of like figuring out what's useful for certain types of proteins. Now, like
Hmm.
the chemistry is ubiquitous and it's everywhere in the world. It's in your clothing, it's in your food, it's in like whatever products you use and the materials you use. Um, and so what I needed to do is I branched out to my entire network of grad students essentially.
Hmm.
And we all study these chemicals day in, day out through our labs. And so I could tell like what's most relevant because they read the literature the most, and same thing with me. And so I'll go through the README just to see that you can um, understand the network. And so
post a link to that in the chat.
um, what I did is I started electing all these papers from people and started writing the molecules in there. Now, the data could come from a variety of formats. It could come as just drawn, or and I would have to like redraw it and then get the name, or it could come as like an MDL file, which is like a molecular data file, or like a CSV file, and then you have to kind of figure out how to mine all that data. And so all that data really comes from these papers, where these
Mhm.
molecules are the most selected as like emerging trends for um, us as a population. So, for example, this paper here, it's called Rings and Drugs, specifying these are the molecules that most likely pass FDA phase 3 trials.
Ah,
Um,
okay. Yeah.
does
Yeah.
that make sense? So, like, it gives
So the,
you a region to kind of look at.
mhm. So
Um,
it collects information basically from all these papers about I mean about these chemicals that are around, and it gives you, you know, like a, I guess like a, yeah, well, knowledge graph, metadata information about the chemicals, and then, you know,
correct.
yeah.
So the main pain point is actually getting the data in the first place. And so I'll show you an example of so this project's always ongoing. It's kind of infinite. Um, but I'd like to show you as we're building the data, we argue about it,
Hmm.
and it's argued in public. So it kind of gives you um, if I can 1 second, so you can kind of see the network here is a little bit
Yeah,
nuts,
that's
but
okay.
um, we argue about what these things should be. So not everything is correct here. And you can kind of see here, this is me and someone else, as we kind of figure out like for these certain reactions that we classify as like the most common reactions that people use in synthesis.
Hmm.
Um, we're trying to figure out how to write it into the dictionary. And this is kind of which, and it's all done in public and anyone can do it. And so, and it goes through the whole process of review issues and then, you know, pull requests, etc. But like it has that format of like where the data is malleable by anyone, but it goes through a formal review process
Hmm.
if someone disagrees.
Yeah.
The difference between us and I think PubMed and a lot of those platforms is the fact that anyone can do it.
Yeah.
Um, and one of our
That's cool. That's very, very inclusive, very, very open. I mean, in the end, this process is, you know, I guess peer reviewed in itself. So it's okay if it's done by a bunch of people, or if it's done via some committee. But I think it's the process that is relevant and makes the data then, you know, true for everybody, and workable for everybody, because, you know, if you are you know, importing data from somewhere, you always have to go, you know, if it's especially if it's just some random data from somewhere, is you have to look at it and see, okay, does it make sense, is it actually correct, or is it some, you know, errors there. And if you know, if it's already done and if it's approved, then this is what makes sense. At least this is the term, this is the chemistry, this is the label, this is the use case, or this is the approval, whatever else, then
yeah,
it's already visible.
yeah, that was it. Um, that was I as I go through more and more of that data, I found errors in other people's databases, but like that's okay because there's also errors amongst my own database, and yeah, you'll actually see Neo4j illuminate some of that.
Yeah.
So I was like, okay, like that's a good way to show how the tool can be useful to fix your own stuff.
Yes.
Uh, but yeah, like that was more or less the idea is because I knew for me I can't actually I wrote a lot of those smiles and I abstracted it a lot from different places. and a lot of people showed me which molecules to pick, and then they wrote the other half of the dictionary, which was the names, and we were trying to figure out a common chemical name. So like when I talk to general public, the other idea is that we wanted a name that most likely resonated with the people. And if I say ascorbic acid, it most, like, a lot of people relate to that in a scientific realm, or if they've been in that space. Whereas if I say vitamin C, it just clicks with the general population more, and also the scientists as well. And so our goal was to kind of come up with a language that was more flexible in terms of speaking it to the general population. So we wanted to remove things away from that didn't sound like natural language. So like IUPAC, which is like the standard nomenclature, it's not speakable. But what I figured out as I was reading through, so in America, they have this thing called the chemical rubber company. Have you ever heard of it?
No, must admit I haven't.
So the chemical rubber company was a manufacturing company doing a lot of manufacturing of stuff. And like they published a lot of books on like chemical and physical data. And so like how that data was all like abstracted, I don't exactly know, but as I was reading through it, there was like this slang terminology that they came up for chemical names. And and maybe the slang terminology came from the workers that were working in the place and they needed some way to talk to each other. I don't exactly know how that terminology came about, but I saw that it was more natural to speak, or they could play the language in a way. And so our goal was to kind of move towards something like that.
Yeah.
Now, like, granted, it kind of it's a little bit tricky because as I was moving into more material science, they had their own ways of naming compounds, and they have
is super hard. I know I talked to a customer who is doing paint a couple of months ago, last year sometime, and it's like, okay, every department has a different name for this, and then there's a number. So this is just inside one company, but it's like, okay, this is paint number blah de blah, and this has the name, I don't know, cobalt blue or whatever, and this is like approved for maybe for toys for kids, or is not approved for this or that use case to be in contact with, I don't know, something else and stuff like that. And it's like, okay, but then the other department inside the same company used a different name for it or something. It's like, this is already crazy. And now with all of that, it's
so I found out that there's a lot of different names for different departments as well, and you're right. But the most important part is what names were given to the public is how I can start to filter it, because everyone has their own nomenclature, but like what products are the most common to the public and what names are being given to the public. And by using that filter, I could kind of control the data explosion. Does that make sense?
Yeah, that makes sense. Yeah.
So here's an example of the FDA releases what color additives that they use for food and cosmetic products in the USA. They have their own nomenclature, FD&C blue, number 1. And these are actually the names that they put on the product. Now, now these names don't ring a bell to anyone. And yet they're used in our thing. So, but I decided to take their names and actually record it as such to write the molecule that's associated with it, so that we have a reference at least for their name.
Yeah. I guess because it's probably something like a standard, and some other company that uses this color may call it differently, but at least refers to it in the back again. Okay, we use FD&C blue number 1, we call it shiny blue, and this,
yeah. So it actually took me a long time to map out the color correctly. it was using the color. I had to use the color index number, because sometimes when I type in the name, it wouldn't really give me what exactly I wanted, or it would throw me a lot off. So it was a little bit tricky to find. And then the other goal of that was to start linking it to the World Health Organization, to what was being mapped to there, and like if they have their own nomenclature, and trying to figure out that mapping. But the WHO and the FDA are what's given to the general population. So that work is actually valuable, if that makes sense.
Yeah. Yeah.
Because you need to, otherwise, like you could be stuck just doing work for no reason. Like you could mine molecule data for forever, and it could be not useful. So that was the premise, is kind of like create this government where basically like we have all these different teams. So I recorded molecules. So cannabis sativa. I wrote all the 425 ingredients to that stuff. And so, I know that, and if you go into a dispensary, there's like 11 terpenes that they classify, but for me, I classify 101 terpenes. So like,
Okay.
my lists are very different. And then I actually work with some cannabis partners that are helping kind of create like ways of using that data for their strains. The sex product industry became interested in what I was doing because if you know so in the United States, we have something called the FDA tainted sexual enhancements list. I don't know if you're too familiar with this.
Must say I'm not.
So in the
But
FDA,
I can guess it's probably something with getting
yeah. So when
stuff inside your body or touch your whatever body parts, then I guess it needs to be safe to do
yeah.
so.
So in it's kind of weird in the United States, but you can kind of release products as like supplemental, that don't have to go through regulation control as much for the FDA. But like,
Okay.
and sexual enhancement products are a little bit different. We have a lot of weird ones like Rhino or something, and they sit in the gas station given to the general population. Now, like sometimes these products don't have to go through like how the law is set. They don't have to go through regulation with the FDA, but the FDA can flag them because they'll test their products for other things. Now, like things like Viagra that was hidden in the ingredient. So you'll see these public notifications all the time, and you see how frequent it kind of is. And our general population actually takes this without knowing that it's in there.
I see. Okay. Yeah. Makes sense. Yeah.
And so I started tracking all of these products as
These
well,
names are
and all
amazing.
these names. And I put it as a word cloud on Reddit. So here's just the biggest offenders. I could go to my Reddit later, or I could share that somewhere. But
Yeah.
yeah. So obviously that gained the attraction of like these guys, because they're like, okay, who's this kid sitting at the edge of Baltimore Street, tracking things away? But if you go through and you check out the names of these things in here, they'll actually give you the names of the chemicals, which you can name to the molecule.
Yeah. Okay.
And so I started tracking these and mapping it to the company, whatever Jack D is. No offense to them, but they're on this publicly anyway.
Yeah.
So yeah, so I started to kind of extend out to all these different industries who got really interested in our thing, in our product, of just mapping out these chemicals. But the really reality of it was that we kind of all talk to each other, like we have this
Yeah. Okay.
because we needed this community to kind of just help us. And the environmental part is starting to grow a little bit more. If you know that some of your sunscreen that you use, some of the chemicals in there like are really damaging the coral reefs. And so
Yeah.
like what chemicals you use in your sunscreen, which is a very basic general product, is really big. And then also chemical waste and how we deal with that is a big one too. So these are kind of bigger industries in figuring out what chemicals are the best and kind of creating this community behind us.
Yeah, I mean, I think it makes sense. This topic is probably gaining attention because of the public is becoming more aware of this. I mean, I see last time when I went shopping for sunscreen last summer, it was labels everywhere, like as the one you mentioned, like coral reef safe or whatever else, and then microplastics and all of that stuff. So it's really an awareness thing. So I guess they wanna
Yeah.
make sure that they have products available because otherwise I think the public won't buy it
And
anymore.
which kind of gives us the power because the development of the language of smiles, which is what I'm writing in, gives us power in the sense that, like, this is another one, by the way, where I wrote it for the common molecules in space. Um,
Hmm.
I don't know how they got that list in the CRC, but they did. Uh, so, like, the power is that we can actually write the molecule directly, which gives transparency to the product. You don't,
Yeah,
it's not ambiguous by a name anymore. You can't hide it through the pipeline of the name. And the drug
yeah,
goes through so many names anyway as it goes through the whole thing. So that kind of gives back some power to the people to and everyone else to kind of decide by themselves if they want that product.
yeah, yeah.
So where does Neo4j fit into all of this then? Um, so I started experimenting. The data was loose, and as you can kind of see, so I started off originally as a tree. Um,
Yep.
I took data structures 10, 11 years ago, and then I realized a lot of that code that I wrote from a decade ago as an undergrad is actually going to come back now. Um, and so I went back to some of my old course material to be like, how to write a node Python object from the ground up.
Hmm.
Um, and that's kind of what I did. So these are all kind of nodes, and each node in here has the smiles and a regex pattern, which we call smarts. Um, and so it can do kind of like fast substring matching. Uh, and each node is then categorized, as you can kind of see, into a very general classifier. So for skin, I've got sunscreen, and then transdermal and delivery surfactants is drug delivery stuff that we use for the skin.
Yep.
Um,
Okay.
Warfare is these are toxic agents used for killing us.
Hmm.
Proteins, so everyone has their big classes of proteins. I only targeted kinases for now because that's popular, and I don't know enough of that space to expand it. I'm still figuring out a lot of these connections, but you can kind of see how I've been organizing it. And as the data has been coming in, I've been constantly kind of reorganizing this tree structure until it
Yep.
started to make sense. And I always asked everyone on my team. So I have about 20 contributors into the project,
Hmm.
mostly all PhD students. Uh, so it's kind of a network across 6 different universities.
Oh, cool. Yeah.
Yeah, so
Very cool.
we've been all been talking through Twitter and other platforms, and especially during COVID, where we're all at home.
Mm,
Uh,
yeah.
this kind of gave us an avenue to do something that we thought was meaningful. Um, the formulation excipients, actually, one of those people on the network, she read every FDA label on the FDA database and wrote down all the inactive ingredients
Okay.
and came up with the common inactive ingredients. I'm like, why did you? She did that on her own accord, so she had that data by herself. And
Yeah.
then
Okay.
talking about my project, she's just like, I'm like, oh, we can include that data. She's like, oh, great.
Yeah.
I don't know why, but
Yeah.
like it was kind of like a cool thing. So you can kind of see that, like, okay, so the data is very loose and it's very malleable, and each relationship is not really defined. So like, um, I don't really know, like the relationship here is just the connection between the node, but
Hmm.
like the actual edge of that graph that has no weight onto it. It doesn't say that this is more than like this has more weight than this one for any reason. Um, I wrote a lot of functionality in the code to give people ways that they can add weights or edges. So, like, how many molecules are in this list, and then you can kind of detect a valuability from it or something like that. But like the point is that I just set up the nodes and the relationships, and then people can kind of play around with it from there, right?
Okay. Yeah. So
Um,
you basically you create the graph out of this, and then the as a baseline for further
yeah,
work,
yeah. And
or to
so
connect it with some other. I guess could be interesting to connect it. I think with other data, and then see. Okay, I have my data set that maybe is internal, or I have worked on, and I connect it to this one, and then I see. Okay, where's where's the connection coming?
yeah, and then you could actually argue it back with us to be like, okay,
Hmm. Yeah.
like let's change it.
Yeah.
Like,
Yeah. Yeah.
then it all changes. So that's kind of like the fun of it. So yeah, that was, and this was kind of new for me. So I wanted to set up this kind of like I had this data structure, right, of like parents and children. So if you kind of see here, like I call this each a parent, and then these are all children.
Hmm.
And then so when you go through the node, you have your root node, and then you have your first children, and then your second children. Now, like um, each node is only aware of its relationship prior and its relationship forward. And so, like, meaning if I find something deeper in the tree, um, so like this color additives, its parent is food and its children are V's, FDA lists, but it doesn't have a connection to the Global-Chem root.
Okay.
So like each node is only connecting forward and back. Does that make
Yeah.
sense? One.
Yeah. Yeah. Yeah.
This kind of allowed me to control things like it made the software engineering easier where I don't have to figure out things like grandparents, great grandparents, or you know what I'm saying? When you kind of get into that type of nomenclature and then you mix it with tracking in as the data structure, it can get pretty crazy.
Yeah.
And
Yeah, I mean it's a structure, right? You set it up in this kind of as a more like a well structured tree,
yeah,
with no cross or interconnecting relationships in between. So that is easier to handle. And the path is still existing, right? I mean, if even if you wanna in a graph, if you wanna go from, let's say
yeah,
here, what do I see here? Chinese how to live longer to the color list, you can basically go. I mean, you need to go via medicinal chemistry back up, then back into Global-Chem, I guess, and then back down into the food and then into the color again. So the path is there. It's just not a direct link because it's
right.
it would yeah.
The point was for all of that to be malleable.
Mm.
Because my main goal initially when I started this like years ago was just to get the data out there initially.
Yeah.
Because and then as the data grew, I was trying to figure it out as I figured it. But yeah, the path is still there. It can still be found.
Yeah.
And then there's a lot of functionality. So there's about 15,000 lines of code that I wrote last year that's built
Wow.
into this. Yeah, this is
This is
and
pretty extensive. Yeah.
this is just my open source one. It's not even my
Yeah.
Facebook. But the point was that I built a lot of functionality to allow users to have fun with it,
Hmm.
and kind of play around with this data and allow it to extend in many places. But that's um, so so the goal then was like, okay, let's start looking into a database model because the data will scale if I want this to scale.
Hmm.
Um, and so I need to figure out something that's effective. Now, like, uh, first, when you create a tree like this, and then you're building a data structure with a parent-child model, um, it's it's very loose because you don't actually know what architecture to map to. So you need to map to a standard. Someone that actually has built a graph thing before, and then the functionality that exists there, or how it should be, like yours should be similar, right?
Hmm.
Um, and so I originally started off with Network X. And so Network X was pretty easy. I could just convert, like add nodes, so add all the nodes and then add all the edges. And then it kind of gave me this pretty like, I'll run this. So it kind of gives you this like idea of what our
Okay.
kind
Yep.
of looks
Mm-hmm.
like, right?
Mm-hmm.
And so this just helps build the idea of nodes and edges into my functionality. Like this is what I should map to.
Okay.
Um,
Yep.
Now, Network X is not a great connector to other platforms. It's not. It's a vis. It kind of like it doesn't have as much functionality as I'd want it behind it, and it also doesn't have like infrastructure built behind it. It's just a tool.
Okay.
So but it helps kind of move me in that direction. So then, what I started to do was figure out a pipeline which kind of uh, goes with what I'm trying to do, but that's also like lightweight and effective. Um, and so I actually started off on AWS on their Neptune.
Mm-hmm.
Uh, and then I was trying to port my stuff into them, but the overhead was a lot because I set up like the AWS organization. Then I had to get all my friends, or not friends, but the collaborators, all their keys and everything, and
Okay.
then teach all the scientists like
Yeah.
AWS in the first place. Then also teach myself and then get my data on there. And then it was taking so much time that it was like 4 months in, and I just didn't really make as much progress because of the
Okay.
overhead I
That's not so good. Yeah.
yeah. So I was like, okay. Now Azure is something that I'm familiar with in the past because when I was doing the startup, we got 100K in credits to build on their platform
Okay. Yeah. Yeah.
because that's what they do. They extend out credits to start.
Yeah. Yeah. Yeah.
Um, and Azure is actually kind of easier for me because I know how to shut down everything with one button. Um, and the main connector from Azure was their Neo4j. Um, and when I was starting to browse for Neo4j, I actually found someone else's blog post on how to connect to it. And I was like, this actually doesn't seem too bad. And then the way that they're kind of writing their queries is very similar to some Postgres, or it looks like it. So I'll just kind of mimic it and
Mm-hmm.
then see what I can do. And then ultimately, of course, you've heard of that ChatGPT.
Yep.
So I started playing with it too.
Yeah.
And me as like, a chemical language person, I started putting stuff into it to figure out like, okay, how does it actually like to talk back to me? Chemical language, does it stick to IUPAC, or can I change it to stick it to a common chemical name that we all know? And so my goal is to kind of like figure out. I don't know if Azure and ChatGPT are going to be linking at some point with their OpenAI. Um,
I would
but those,
assume they would. I mean, Microsoft today, I think they announced they will invest significant amounts of money into
yeah,
OpenAI. So I would. I mean,
and I saw
well,
their subscriber, so their ChatGPT Pro is like $42 a month,
yeah.
and then you can use their API.
Mm, yeah.
So I was like, okay, there's something that's kind of building here, and maybe if I put these infrastructures in place, it could something will happen.
Yeah.
Um, so it's a little it's pretty easy if we just kind of look at the code. And I know that it looks a little funky or Python heavy. uh, so I apologize to that. I also was writing this like pretty fast in that day, and so anyways, the so um, in Python we have our class objects, and you can kind of set up this Neo4j connection object, and all you really have to do is pass in the where the Neo4j instance is and the username and password. Or if you have like an existing uh, database that's already running.
Okay.
And when I saw that that's all you kind of need, it's pretty easy to just connect right into it and then start pushing your data through. Is like it's an easy concept. Um, The thing that I wanted to do very simplistically was just add all the categories that I had and then all the molecules that existed within them.
Hmm.
Uh, and so I have these two functions, add categories and add names, which basically goes through my data. So I ported all my data to a TSV file. And it kind of allows other people to basically also just take this data in its raw form and play around with it. It has the name, the molecule, and then I think, sorry about this.
I think if you or if you click on
Yeah.
raw, then you see or there, yeah.
There you go. This works better.
Yeah.
So the name, the molecule, the where it came from, and then the one parent above it, so it's category, and then the full path.
Okay.
So that full path is kind of what metric we'll be using as our, or is that's the main metadata point in our whole connection point. Uh, so basically, I read in the data, pass in the path, and then add the categories and IDs. So basically, just sets up all the names. And then this is the connection point. So all you really have to do is pass in that IP address, your username and password, which I don't mind because it's sandbox, and then we go right through.
Yeah.
Here you're going to see this kind of create constraint flag, and this is a really important thing to understand, which is when you create like databases like this, we want to make sure if records are going to be unique or not.
Hmm.
And one of the things that we need to keep track of when we do this data is that when we map a name, it should be the same molecule. Um, in Smiles, when you write the molecule down, so like let's say if I was writing propane, the propane is the 3 carbons, and it's basically just looks like this, all linked together. Sorry. And then you could also write it though like this. And then
Okay. Yeah.
they both map to the same name. So they both
Hmm.
to this.
Yeah.
Um, we wanted to make sure that the molecule was, even if it existed across different nodes, that it still retained the same smile structure to the name, if that makes sense.
Yep.
And so that idea of uniqueness, a formal database actually kind of brings that for you when it's harder to control yourself. So in the last year, right, I wrote about 3,506 entries. Uh,
You've
when
been
I
very busy.
yes, so now going back and looking at that list, I'm actually confused at my own work sometimes because maybe I've forgotten some things here and there, and then you do some work one day and then you move on from it, or maybe I get distracted. People say that often. I don't know, but I need something to check me. So that's another really big reason just to have this formal database behind you, so that we can kind of like ensure these categories are unique and how they map.
Yep. Absolutely.
And so I did all this and added the categories and the names. And the first thing, oh, it's right here. So in here you have your, it was easy just to kind of like view the data at itself. And you can kind of see that I've got this category and the molecule and the name. So these are the points that I had in my TSV file.
Hmm.
And then it's now linked into the Neo4j. And so if I go into the category, you can kind of see here, like these are the different categories, like it's linked up. Like this is the root node, which is the
Yeah.
Global-Chem,
Mm-hmm.
and then miscellaneous. So the point is just to like have all the nodes first, like exist.
Yep.
And then from there, we'll start setting up connections and
Mm-hmm.
how
Okay.
they all kind of map to each other. So now that all the nodes exist for the categories, the next step was to just pour in all the molecules as well, so all that data. So
Yep.
you can see them here. And so it's kind of like, this is where it helps me like kind of build this out. And the relationship was then through the category to the molecule. And it was only one step down, if that makes sense. I couldn't build the full tree just yet because I was still doing this as I go.
Yep. Okay.
So I'll kind of show it to you how it looks like in the bloom. So there we go. I like this aspect where it's pretty easy. Okay. So I'm just going to query the molecule to the name for now.
Okay. Yep.
Okay. So here's all the data, and a better way would be through the hierarchical layout. So
Okay. Yep.
yeah, so sometimes like, okay, the circular one looks pretty.
No, yeah, it's not for this. This is definitely. I mean, this. Yeah, this is why it's there. The different layout. Yeah, this was
Yeah,
one.
this so I can kind of like talk about this a little bit more in some
Yeah.
depth. So the molecule name here is like benzene. And then it's saying that this name exists in all these different places. So
Mm-hmm.
benzene exists in maybe 8 different nodes, which makes sense because benzene is a very common molecule. It's the root.
Okay. Yeah.
As you can kind of see, as we get to more and more deeper, different types of molecules, things that, so this 5-methyl indole, which sounds a little bit not as common as benzene,
Mm.
only exists within one node. So
Yeah.
it starts helping me map out, like, okay, how many of these molecules exist in several different nodes? And then do they all link at the same smiles? So originally what we were doing is kind of figuring out, like, okay, through the GitHub, using GitHub Actions to kind of like filter through it and scroll through all the nodes and map the names, but it got a little bit too hard to control. And plus the GitHub bots, they don't shut up. Um, um, yeah, so we had all these like checks on ourselves, where we basically like, for example, I go to our actions. So you have a lot of different bots checking out stuff on
Mm-hmm. Okay.
the
Yeah.
software. And it's mostly just me coding these bots. When GitHub Actions got released, I went a little bit crazy on the platform, I guess. And at times some of these workflows would fail, but I had things where, like, if the FDA color list ever changed, like this bot will check it and then notify everyone.
Mm-hmm.
But yeah, so it was like kind of this check with the system. But yeah, so with the bloom, what I started doing now is realizing like this first step where all the names and molecules like need to be mapped out correctly. And so I actually stopped here and went back to my collaborators, and when we started curating lists. So everything that was illuminated here, we started filing as issues, like making sure that the smiles were retained.
Mhm.
And so this is our first step into the whole data curation, to kind of gunning it. Uh,
Yep.
the we have other collaborators where basically, so we have these models that we're starting to train and figure out, but we're realizing we need a lot more data than we already have. So we need about 3 times as much data.
Mhm.
Um, but we have also realized that from this own display that we need to take a pause and go back and curate our data before we move forward, and also make it more aware to everyone. Um,
Okay. Yeah.
because uh, yeah, that's been our pause. So um, that is my full case.
Yeah. Very, very cool. So I guess thank you very much, Sul. I mean, this was cool, and very, very interesting. So if people are watching this and think this is interesting and wanna participate, where do they go?
Um, so GitHub is our primary source, where you'll always find, like, if you even type it in Global-Chem on Google. So
Yeah.
if I just type in Global-Chem, oh, it's about fourth on the list.
Cool.
And so you can kind of just find us there and file issues as you see fit. We have a Discord that's available, so people can click the Discord button
Mhm.
and head on to our servers and talk to us. So we have a full team on Discord, that we're always chatting. Twitter, I'm on there, and LinkedIn. So there's ways to kind of access a lot of us. Um, you'll find all the contributors to the project over here,
Mhm.
and you can kind of reach out to any of these people as well, and they know about this project or relay you to me. Um, and so if you want to contribute, though, so one of the major things that we're actually setting up is, a way to submit your data to us. Uh,
Mhm. Ah, interesting. Yeah. Okay. Yeah.
uh, so there's a website that we're developing that basically you upload your names and your smiles, and then what object it links to, and then submit it for when it submits review, it would be submitted here as an issue. So then it would just send the request to us. So then
Yeah.
that way, people can just upload data, and it doesn't have to be smiles. It could just be their list of names, and then whatever object it links to, and then we evaluate it,
Okay.
or we write the smiles for it,
Yeah.
or gather that. So it gives the general public access to doing that. Our major platform that I've used to kind of gain traction is through Reddit. Um, and so Reddit is how I've kind of like gone about, showcasing a lot of that stuff to the general population.
Yeah.
And the goal was to kind of entice the community. Um, And so I'll go here to some of the most things that I've ever put on Reddit. Um, so when I first started doing a lot of this, like, data visualization and things like that,
Yeah. Yeah.
um, so they got really into it because they can kind of see the beauty in some of this stuff. Um, and then also
Absolutely.
they became, like, very aware of what's going on. And
Yeah.
so um, so I used a lot of that community to help kind of figure out things and teach people things about stuff. So you can find this a lot on Reddit, and I use Reddit to find the common names because it gives me a way to talk to the general population, like an open source platform to talk to them.
Yeah.
I find Twitter is a very big conference room where everyone's just tweeting, but, like, um, it's not very, like, a casual way of talking.
No.
You
Yeah.
want to write
Yeah.
longer messages.
Yeah.
And then I also found that talking through journals or like a scientific journal, not many of the public has access to that or know how to get access to that.
Hmm.
So they can't talk about it as much. So they read popular science on top of it. But sometimes they also don't know where the open access papers are. So I also go to Reddit to just show them like where these papers are, or if they have like different symptoms, or also just this kind of resonates with more of a college people, but like if you want to see my GPA over
Yeah.
time, kind of gives them like a more personal aspect that we're all just normal people.
Yeah, absolutely.
I,
No,
I,
this is very cool, and I think especially the visualization is always. I mean, that's here at Neo4j is a very clear winner. So when I see this, more people understand, especially with you know compounds and proteins and chemicals and all that's in that corner of the world.
yeah,
There is so much knowledge there, but there is in so little awareness or so little knowledge at the same time. So there's so much information, but so little that people are actually know. So like you said, I mean, vitamin C everybody knows, but then again, if it goes already a little bit away from that, it's like, ooh, I have no idea what that is. So
it's funny how much
yeah,
that can really change, over time. Like
yeah,
I use that ascorbic acid example a lot because it actually it works a lot. Like the people that are not in the science space, you'll see that they don't know what that name really is.
totally, yeah, yeah, yeah.
Yeah, the visualization really helps with capturing the people's interest initially,
Mm,
or also making blatant statements like the 400 chemicals inside
yep.
marijuana. Kind of.
Yeah, yeah, and then you can visualize it. Yeah,
Yeah.
that's good. Okay, cool. I don't see any question from chat. I have one more to maybe
Mhm.
before we wrap it up is like next steps. I think you mentioned a little bit. You need more data. You will import it, incorporate the data into Global-Chem, and then in the next step, I guess they go into your into the database. So what's other than that, what is a next step for Global-Chem, and maybe in particular connected to Neo4j? What does Neo4j bring for that?
So I Neo4j is going to bring the stability, but as well as the connection into the other machine learning operations. So like when you have this
Hmm.
data, we're starting to get into a field of where basically you you'll have all these molecular descriptors kind of describing like what the data is. And so a very common thing, like descriptor that I want to say is like this log p. Have you ever heard of this before?
No.
So when you're designing drugs, let's say,
Yeah.
um, you want to test its a drug's solubility as to whether it can be soluble in water or something that's like not.
Okay. Yeah.
And so we use it as a descriptor based from the smiles, which you can predict.
Hmm.
And a lot of these properties can all be done in a very common open source tool called RDKit. And so these pipelines I've already built into
Hmm.
the Global-Chem thing as Python packages. Um, and so the goal now is to start predicting new chemical space based on these different descriptors of our data. And when these models could be pretty tiny, but I wanted a robust infrastructure first in place. Um, and I needed a way to scale it into Azure. And so the the next goal would to be is to first refine the data, curate it, and make sure it's effective, and then port it into the Neo4j, and then test out different descriptors or my descriptors that I'm using
Mhm.
from my own research, and then scale it on the Azure using Terraform or something of that nature, where I can kind of build like a mini little cluster to build these like pipelines continuously.
Okay.
I have a feeling that if I have that infrastructure built, other platforms like the Chat GBT or whatever will fall into place, or it'll make it easier if I want to go down that route.
Mhm.
Um, my goal is to make the Azure Neo4 connection and then scale the data. So scaling is my next real big priority.
Cool. All right. Very, very, very exciting. Oops.
Sorry.
That's okay. Very exciting. Very, very interesting what you're doing. I think that was a great session, Sul. Thank you very much for the overview. Thank you very much. Obviously, in the name of all the users who will, benefit from you making this public and from you working on the on the data. So yeah, I can only repeat, if you watch this, if you think, oh, this is cool, I want to participate, then please please check out the GitHub repository. Hit up Sul on Reddit or Twitter or on his blog, and get in touch. All the best for the next endeavor. So if you ever have a the pipeline to Chat GTP up and running, then I think we should do another session and do a live stream with Chat GTP.
Yeah, that'd
And
be cool.
that would be fun. Yeah, I think that's it for today. Thank you very much all for watching live. Thank you very much, Sul, for joining today, and have a great rest of your week, rest of the day, and I'll see you soon on another live stream sometime somewhere. And yeah, thank you all for watching, and take care, everybody. Bye bye.
Thanks, Alex. Bye.
Thank you.